What's going on here? Okay, so we have just kind of got started into our unit on equilibrium, right? We've had a couple of lessons on it. We talked about what it means for a reaction to be at equilibrium, and you just handed in your little assignment that hopefully illustrated it. Sometimes the idea gets lost, but in the end, I'm hoping that you realize that in your last three transfers, didn't matter what the size of the straw was, you were transferring the same amount, right? And the size of the straw kind of determined, how much was in each of those cylinders, but still the same amount was being transferred. A couple of important things to get from that. Equilibrium is attained when we have the forward rate equal to the reverse rate. In other words, the amount of reactant becoming product is equal to the amount of product that's turning back into reactant. Another thing that you hopefully got from it was that at equilibrium, you don't necessarily need to have the same amounts of reactants and product. It's a balance of rates and not of concentrations. So they definitely do not have to be the same, all right? And those are the big important things, that when equilibrium is established, we've got this forward rate and reverse rate the same, and then we've got this certain amount of reactant and product. Last day I introduced to you something called the ICE table, and that's a way in which we can calculate concentrations at equilibrium, given some initial concentration, some kind of change, and then a final concentration. And then I introduced you to the equilibrium constant and the equilibrium expression law, and we're going to continue on with that here at this point. So, again, the equilibrium expression law comes from the balanced chemical equation, all right? And it's simply an expression of the product molecules concentration over the reactant molecules concentration to the exponent that's determined by their coefficient. We only include gas or aqueous phases, and that's because solids and liquids, pure solids and pure liquids, have constant concentrations. And I did a very quick calculation to illustrate that to you the last day. The example I used was water and liquid water, and if we start with the density of water, 1 gram per milliliter, you could easily calculate what that moles per liter value is. It's around 56 moles per liter. And every pure solid and every pure liquid, if you were given its density, you could calculate its concentration in moles per liter, which is essentially a measure of how the molecules are packed in that solid or in that liquid. What it comes down to in our equilibrium expression is that we don't include the solids, and it's only the factors that can change in concentration, gases and aqueous solutions, that we include in the equilibrium expression. And I kind of rushed through this. You don't have to write this down, but I'm going to just quickly go over it as an example. So if we're looking at this one here, the equilibrium constant for this one, again, always products, N2O4 over reactants, NO2, and again, the exponents come from the coefficients. All right, very straightforward. Liquid gas, that's the one I did very quickly at the end. Again, K is equal to the concentration of H2O gas, and that's it. We don't have the liquid on the bottom for that. That's kind of interesting. That means that the amount of water that can evaporate in an enclosed space, in a closed container, is not dependent on the amount of liquid water that's in here, but it's only dependent on the pressure that the water then creates, or the gas that the water creates as it evaporates. The amount of liquid is immaterial, all right? It doesn't even come into play. And if I have something like this at the bottom as well, so in this case, the concentration, and this is a dissolving situation, the concentration of Na plus, all right, squared times the concentration of S2 minus to the exponent 1. And again, an aqueous situation, the amount that a substance will dissolve has nothing to do with the amount of solid that's sitting at the bottom. It has only to do with the concentrations of the ions in the solution. Has nothing to do with how much powder or how much crystal is sitting down there in the liquid undissolved. It has everything to do with the concentration of the ions in solution. So there's some quick examples. I didn't have time to go through those. I wanted to jump ahead to the homework problems and to that example. All right? So again, leave out the liquids and leave out the solids. It's that simple. Okay? All right. And then I gave you a little bit of homework. It was not very much. At least I hope I got this slide. Did I give you this? All right, good. All right, let's now talk about, I want to talk about three things today, hopefully three things, if there's time. I want to talk about what this K means, right? What does it mean if if the K value is big, and what does it mean if the K value is small, and what does it mean if the K value is close to 1? Then we're going to do some simple calculations where we're going to calculate the value of K. And then if I've got time, we'll see what the time leaves us. I might go ahead and talk then about the next calculation, which is the system at equilibrium? All right? Now, just a little look ahead. We're going to be doing probably 4 or 5 different variations on calculations in this unit. And so what I'm going to do is I'm going to try to separate them out as much as I can. We'll put them on a little piece of chart paper so that you guys get smarter, you know the way that works. Anyway, and we'll try to make sure we very, very clearly define which method of a question or which method of solving a problem you're going to use. Because on the test, I'm not going to say, oh, by the way, this is where we're solving for K and we're starting with equilibrium concentrations, right? I'm not going to tell you what tactic to use. So you're going to need to be able to recognize them. And so I'm going to try to, as best can, you know, separate those different tactics out so that you can figure out a way in which, in order to determine which method to use, right? Because it can get a little confusing. Okay, no calculations yet. All we're talking about now is what does the value of K mean? And I've already wrote this down once, but it's good to write it down again. When you're thinking of the value of the equilibrium constant, and you're not thinking of it in terms of an actual expression, this is a very quick and convenient way to think about it. It's simply the amount of products, or the concentration of products, over the concentration of reactants, all right? And so we can come up with some very easy relationships here. You'll notice that K and the products are on the top. In other words, I can turn this equality into a proportionality statement, all right? And I can say then that K is directly proportional to the concentration of the products, all right? I could also say that K is inversely proportional to the concentration of the reactants. The neat thing about an equilibrium, though, as soon as you define what happens to the products, the opposite thing happens to the reactants. So we really don't need to worry about this inverse relationship, because that can sometimes be a little confusing. It's an opposite scenario. So I would prefer you to think about the direct relationship. K is proportional to the products. And now I'm going to give you 3 slides that contain way too much information. But if K is proportional to the concentration of the products, if the K is big, how much product do I have? A lot. There you have it. That's the logic right there. If K is related to the product values, if K is big, we have a lot of product. That's it. You've got this relationship. Again, way too much information sometimes, but there is some good information on here other than just saying a lot, right? If K is large, then we have a lot of product and not very much reactant. Another way of saying this is that we say the equilibrium lies to the right. So now when I say the K is big, I'll say, oh, well, the equilibrium is way to the right. It means that We're getting a lot of product. Another expression we like to use, the reaction favors the product, as if it's got some kind of a conscious, I like you much better products. I'm going to make a lot more. That's just, again, another saying. Another way of thinking of it, the reaction essentially goes to completion. It's almost like it's a spontaneous reaction as opposed to an irreversible reaction. Sorry, it's almost like an irreversible reaction as opposed to a reversible reaction. As if it goes to completion. So when K is large, and again, simply think of that relationship, products over reactants. When K is big, there's a lot of product. Here's an example of a reaction with a very large K value. O3 decomposes to produce 3O2. And you'll notice, and we're looking at the exponents on the power of 10. When we're talking about large and small, we're not looking at that number up front. That's just the little details. That just gets us the fine values. But we're looking at the powers of 10. 10 to the 57. It's huge. At 298 Kelvin, which is room temperature. And that's a good thing because our lungs prefer oxygen as opposed to ozone. Ozone would not do good things to our lungs. So the concentration of O2 to the power of 3 is much greater than the concentration of O3 to the power of 2. But what to take from this? When K is big, there's lots of product. Now, just looking ahead, if I do get to number 3 on my little agenda here, we're going to be asking ourselves the question in the near future, is this system at equilibrium? Now, that's a little different question than this is at equilibrium and the K is big, all right? In a question like this, we're saying that it is a large K. In a question of, is it at equilibrium, we're asking ourselves the question of, are the concentrations big enough to be at equilibrium? Those are different situations. This is an is and like now situation. Those questions are like a what if. What if we had this? Is it at equilibrium? So that's going to be slightly different. I just want to differentiate between the two. And my next slide, what if K is very small? And we're just going to flip everything around because that's exactly the case. If the K is a very tiny number, reactance is much greater than the products. Again, I encourage you to think about the product relationship. If K is small, the concentration of the products is small. And if there's not very much product, it means the reaction kind of didn't go anywhere. We put the reactants in, we put it in a closed container, we say go, start your reaction, and it hardly goes anywhere. Very little bit of product is produced. We say it lies to the left. And when I say the left, right, when we write a reaction, it's reactants on the left, products on the right, so it lies to the left. We say that it favors the reactants. The reaction does not occur to any great extent. In other words, it doesn't really do anything. Yep. No, No, my next one is what if it's about 10 to the 1 or 10 to the 0? Yeah. No, they can be any range. Yeah. And really, when we get ahead into doing these calculations that I've been describing to you, these different types, it's that size of K that determines what tactic we use. Yeah. And if it's in the middle, then we've got to use a particular tactic. Yep. We can take shortcuts. If it's really small, we can take shortcuts. Yeah. Okay, so this reaction 10 to the minus 25 hardly didn't go anywhere, which is a good thing because in our atmosphere we've got nitrogen gas and we've got oxygen gas, and just at room temperature, very little bit of NO would be produced. I'm pretty sure NO is nitrous oxide, which is also used for what? Anybody know what we use nitrous oxide for? Yep. Yeah, it's laughing gas. So if that equilibrium was like different, then we would all be laughing a whole lot more at room temperature. But we're not, so just keep it down. Okay, not very much nitrous oxide in the air. All right. Okay, that was bad for a Monday morning. Maybe I should have had some laughing gas in the room or something. What if it's in the middle? And you'll notice approximately 1, and that's where the question is, what is approximately 1? What is really big and what is really small? And when we get doing these questions, there will be a little test that we can use to determine what is big and what is small. It really depends on how much of the stuff we have, whether we have a large amount or a small amount. And if K is close to 1, then we have a little bit of product and a little bit of reactant. Again, we're talking about a logarithmic scale here, right? We're talking powers of 10. 1 is being the middle, and then all those tiny little numbers as you approach 0, right? And then 1 in the middle with all those, big numbers as you approach whatever, infinitely large. And you'll notice here we've got 5.09 times 10, or sorry, no times 10, 5.09 times 10 to the 0. Close to being 1. Okay, so now we've got a handle on what it means to be large, small, et cetera, et cetera. Now we're going to just do a couple of very simple examples. We're going to calculate the K. These are the little baby steps of our calculations, right at the very beginning. Going to come in 2 types. First one, they give you all the equilibrium concentrations. We find the K very easy. Second one, they don't give you all the equilibrium concentrations. We use an ice table, and we get the K. Sorry. That's noisier than I thought. The black one was failing me. All right? Like I said, a little overdoing it to just, state the relationship that K is proportional to the products. But it is important that we use the terminology lies to the right, lies to the left, or sits in the middle. Okay, there is a couple of questions that deal with the size of the K value. It's very qualitative. It's very straightforward stuff. Again, these next two examples you'll have to write down, and then after that we will be getting into, I have a page that has the examples on them so that you don't have to write them down, and then we can go through them a little quicker. These first two examples still don't kind of fall into the realm of what I would call the main examples of doing these problems. Looking in the drawers here, I'm seeing I've got some tests. I got one I can return. That was out of 19 instead of out of 20. Okay. Sorry. Like I said, this is the baby steps of the calculations that we're going to do. This is still part of that lesson that we started on Friday where I introduced you to the equilibrium expression law. And in this situation, we have a particular equilibrium. There's the reaction there. And you'll find in many cases the reaction isn't really our focus of concentration. We're not necessarily, going to be really focused on this. I give you the balanced chemical equation because I don't want you to worry about whether it's balanced or not, all right? And you'll notice here we're given the equilibrium concentrations and we're given this data for all of our reactants and products. And if I were doing an ICE table, what I've essentially given you is I've given you all the E's. I've given you the bottom numbers because it says at equilibrium, all right? If the question says at equilibrium, the concentrations were found to be, we've given you the E's. If it says the initial concentrations of the reactants and products were, then we've given you the I's. And the C's, remember, are simply determined by the coefficients with the X, with one being negative and the others being positive. Pretty straightforward. So if we're given the E's, then the ICE table is irrelevant in this situation. I'm given all of the answers to the equilibrium thing. So if I'm asked to calculate K and I've given all the E's, no ICE is needed in this. We don't make an ICE table. We don't need to go to that extent. Really, all we're doing here is writing down the equilibrium expression, we're putting the numbers in, and we're getting a value. Substitute and calculate. Now that's the simplest of the simple. It will be more complicated than that. I'm going to continue this going, by the way, folks. So I don't know if you want to try to put this on a separate page, to summarize, because I'm going to just keep adding on to this every time I get a new type of problem so that we can differentiate between it. If some of you have wrote it down, that's great. But if you want to put like an equilibrium calculations summary page or something, that's what this is going to become in the end. You could wait till later and copy it all down later on as well. It doesn't matter to me. I'm not going to get through it today, right? This is just my first example. But every time we come up with a new scenario, I'm going to write down kind of what we're thinking when we look at the data. So, equilibrium concentration, I'm given the E's. There's my number. Therefore, I'm simply going K is equal to, I'm going to write down an equilibrium expression law for this. They're all gases. HI squared, H2, and I2. And sometimes, again, I don't care if you write down the data or not. An ice table is really a collection of data, right? An ice table is a formal way to kind of gather it up. Here we don't need the ice table. I don't need you to rewrite this. Just put the numbers in and start calculating. So what do I have? Found to be 3.11 moles of HI, 3.116. And notice it's moles per liter. It must be moles per liter. So I can put that in there. When I put the numbers in, I change from square brackets to round brackets because remember, square brackets represent concentration, and the curved brackets is what we use in mathematics. If you had square brackets in there, it wouldn't be wrong in any way, right? But we're going from a concentration to a mathematical expression. We put the squared there. H2 is 0.422 to the exponent 1, and this is also 0.422 to the exponent 1, and we calculate and we get a K. This is the way scientists would determine K values. They'd put some reactant in, they'd close up the reaction vessel, they'd let it come to equilibrium, they would do their measurements, whatever measuring techniques they use, and they would determine final product concentrations and calculate and get a K. It's as basic as it gets. And do we have a value? Yep, what do you got? 54.5? 54.5, 3 significant digits, excellent. And don't worry about the units again. Each K will have its own set of units depending on what the exponents are here. In our case here, the moles per liter all cancel out because I've got moles per liter all squared up top. I've got a moles per liter there and a moles per liter there. Those would cancel all the way. We're not going to worry about units for K. Is that a large K? No, I'd say that's close to 1. That's a fairly balanced situation. All right? We're okay with that? And I'm going to have to say okay and K. K? K, yeah, correct. This is a continuation. Now that we know the value of K, we can substitute other bits of information and simply use it as an equation. So because this is linked to the last question, what was it, 54.6? 54.5? 54.5, I'm thinking of that concentration of water for some reason. Now I'm not going to write this down as a separate example. I guess you could. It's asking, find the equilibrium concentration of HI, and it's giving us the other concentration. Just solve. No ice needed for this as well, right? They're giving us K and the other E's. No ice is needed. Maybe we could write this down as a separate one. I'm going to have a B one down here. But then I guess I could have a 2 right here, right? Find E just 1. So here we're looking for an equilibrium concentration. I'm going to put a B in there. I got a second one in there. But here we're saying, find the equilibrium concentration. Okay. You might be thinking, I need my ice table. I'm going to be, because that's where the equilibrium concentrations are. But notice in this case, we're given K, and we're given all the other E's. So in this case, here we are given K and all other E's. I guess it's not possessive. Darn that English thing. If you're given the K and all the other E's, then all we have to do is sub it into the equilibrium expression. Again, no ice needed. No ice. Just put it into the equation. So this is an example where they're asking us to find an equilibrium concentration, just one of them, and it's given us the K and all the other E's. In other words, they're giving us everything in the equilibrium expression law except one of the E's. Solve for it. Okay? We will run into a situation where it says, find all the equilibrium concentrations given the K. Now that's a completely different ballgame because we're going to be finding multiple things. Here, basic. So again, in this case, the K is equal to the concentration, what was it, HI squared over H2 I2, and the equilibrium concentration of H2 and I2 were 0.5. So in this case, we've got 54.5. We're looking for the concentration of HI. That's HI squared over, and that is 0.50 times 0.50. And now you're doing the math and you're just solving for the concentration of HI. Yep. Did you take the square root when you were done? Excellent. Could you give me what you had of the number before you took the square root? HI squared, and then this times this times this. What do you got there? 54.5 times 0.5 times 0.5. Sorry? 13.6? 13.6. I just want to illustrate for those who are less mathematically inclined, when you've got a square over here, we're taking the square root of both sides, and therefore HI is equal to, now I don't even remember what you said as the answer. 3.7 and to two significant digits, thank you, 3.7. And we do have to include a unit on that. Now it is moles per liter because I am talking about a concentration. And there I will take a half a mark off for a unit missing. All right? Okay, pretty straightforward. This again is the same question, just adding on some steps. Would have been nice if this went along with Friday's lesson, but that's okay. Does anybody remember what the K for the reverse reaction, how it's, what am I doing here? Reverse is equal to, how it's related to the K of the forward reaction? Yep. Yeah, we would actually flip it around, but we have a nice, simple mathematical relationship. Yep. Yeah, it's just a reciprocal of it. 1 over K. So in this case, we're just saying it's 1 over, what do we got? 54.5? Why can't I remember that number? 1 over 54.5. So if you're given a K value for a question, say later on, and you need the reverse for some reason, you can always just get that by taking the reciprocal of it. What do we have there for a number? Somebody got that? Jess, what do you got? 0.018. 0.018. We need one more digit on the back end of that. I think, don't we? 183. Okay. So that's just kind of covering all the bases for just that equilibrium expression. All right? And you'll notice from the title of the example here, and this comes out of the textbook. I took this one straight out of the textbook. The textbook's pretty good. It also, in all of their examples, and if you want to go back and take a look at some other examples, all right, this one's going to be the same because I took it right from it, but it's pretty good at putting a little title with each of the different types of problems you're going to run into. So in this question, we're given all of the equilibrium concentrations. Sorry, we're given all of the initial concentrations. 2.98 moles of PCl3, 8.70 times 10 to the minus 3 moles of PCl5, and no chlorine gas. So here we are given all the I's and you'll notice just one E and just one E. If you're given all the I's and just one E, then we can use that change line to determine all the other E's, which is what we did the other day, right? The other day we just did the ice table just for fun, just to introduce it to you. Now we're going to attach the ice table onto a determining the K situation. So we will use, yes, ice in order to solve this. So this essentially puts together what we did when I introduced you to the ice tables at the beginning of Friday's lesson, to what we've just done here. So we will go through the motions of the ice table, then we'll find all the E's, and we will substitute it into the expression. So the ice table, I need to rewrite PCl5. Notice they're all gases, so at that point I'm going to drop off the states because they're all gases. They're all going to be included. PCl3 plus Cl2. 2-liter container. It's a little mean. If it's a 2-liter container, I need to do a little calculation on the side to figure out how much PCl3 and how much PCl5 there is. This is exciting. It's funny because I didn't do this example. I haven't done it. I just pulled it out of the textbook. This is a little mean. This is kind of fun. I like this question. So first, let's find the concentration of the PCl3. Concentration of PCl3, that's an initial concentration, and I'm totally running out of space here because I didn't think I needed this much space. That's okay. Moles per 2 liters, 0.298 moles divided by 2 liters. Yep. 0.149 moles per liter, and that's my initial of PCl3, 0.149. Oh, this is fun. Exciting. And I need to do the same with the PCl5, 8.7 times 10 to the minus 3. So the concentration of PCl5, and I'm so out of space, 8.70 times 10 to the minus 3 moles divided by 2 liters. Yep, what do you got? 4.35 times 10 to the minus 3. And how much Cl2? 0, right? 0. Excellent. There's my I line, CE. Again, even though they give us that nice number for the Cl2, and you could quickly just do some calculations, it's good practice to use the X. So let's go through the motions. Now, the question becomes, which way is it going to shift? Right? Because sometimes we can have a reaction that shifts back to the right. You'll notice I've got some product and some reactant, but I have none of this product. So you might think that this might push it back to the front. In actual fact, the fact that there's 0 of this will still push a little of it that way. But as I said, it doesn't matter where you put the negative sign. You will always get the correct answer because the negatives will fix each other in the end. I believe that this is going to go to the right because there's 0 of this. Right now, this cannot collide with anything because there's nothing. So it's going to head this way. What that means is my negative is going to be on this side. The reaction is going to go to the right. Negative X plus X plus X. This is going to be 4.35 times 10 to the minus 3 minus X. This is going to be 0.149 plus X, and that's going to be X. I wonder if I've got a clear screen on the next page, because at this point I need some more space. I'm going to use that homework space right there to finish the problem. Ignore the homework. Oops. All right. I'm going to use that space to solve it. So now in the end, we're just going through the regular ice table. I have 2.00 times 10 to the minus 3 moles of Cl2. Well, that is X by the looks of it, isn't it? So X is equal to that, which means I just have to continue and calculate. So X is equal to 2.0 times 10 to the minus 3. X is equal to 2.0, was it 00 times 10 to the minus 3 moles per liter. I don't know what the significant digits were. I just looked at it. Was it 00?
Just moles.
No, it's, oh, did it just say moles? That's great. This is evil. Because if it just says moles, you're right. What's the concentration? Yep. 1. Because I got to divide it by. Holy moly. Concentration of Cl2 2.0 times 10 to the minus 3 moles divided by 1 liter is 1.0 times 10 to the minus 3 moles per liter. And because I can't erase, I get to scribble. That's fun. 1.0 times 10 to the minus 3 moles per liter. Good catch. I missed it. Now I can solve for the rest of them. Concentration of PCl5 is going to be, and now I need to go back and look at my equation. What did I do? 2 liters. I'm all excited about this question because I haven't looked at it before. 2 liters. Thank you. What was the last guy? 4.35 times 10 to the minus 3 minus x, right? Whoops. Go too far. 4.35 times 10 to the minus 3 minus x, which is going to be pretty easy, right? 3.35 times 10 to the minus 3. Is that what we get? 3.35 times 10 to the minus 3. And concentration of PCl3 was what? 0.1, sorry? 1.144? 0.14449, 0.149, 49 minus x, 0.149 minus 3.35. Oh! Is it plus x? Plus 1.0 times 10 to the minus 3. Did I get it right? It's killing me this morning. We got Monday morning all over this. 1, 2, 3. It adds to that last decimal, doesn't it? 0.15. 150. Woo! That was painful. For me, you guys are probably long done the question. And that's good. Now we've got all of our data. Because we've got the CL, we've got the PCl5, and we've got the PCl3. Now we put it in the K. I got to think of the equation. What was it? PCl3, Cl2, PCl5, all to the exponent 1. Is that correct? Check me on it. I'm the one who's losing it here this morning. And PCl3 ended up being right there, 0.150. Cl2 is that one up there, 1.0 times 10 to the minus 3. And PCl5 ends up being there, 3.35 times 10 to the minus 3. Woo! This is killing me. Over there. What do we have? What do you got? Somebody? Anybody? Yep, Ben. 3 significant digits? 4.47 times 10 to the negative 2. Do we like rounding it? Do we like that number? 48. Do we like that number? All right. Oh, that was a little bit of a workout. Why it was a workout? Because they gave us moles instead of moles per liter, which is a good one to review that thing, right? I tripped over that. And they gave us 2 liters. Sometimes they give us 1 liter. It's nice because then it just becomes moles per liter. But they gave us 2 liters, so we had to calculate it out. Even with the final concentration, they didn't. They just gave us moles, so we still had to convert that into liters. Excellent. But in the end, when they give you just 1E, and, when they give you all the I's in just 1E, we have to use that ICE table in order to solve it. All right, there's some practice problems, and I was going to go on and talk about the reaction quotient, but we'll stop there for now. I'll let you work for 10 or 15, and maybe I'll introduce it. I'm not sure. We'll see. We'll see how that goes.